Okay, we're at 55 and counting, so I think we can go ahead and get started. If you're ready, Peter.
Ready?
Okay, so I'm very happy to introduce CGD's own Peter Lauritzen as the seminar speaker this week. Dr. Lauritzen is a scientist working in the Atmospheric Modeling and Predictability, or AMP section at NCAR CGD. Originally from Denmark, he received his bachelor's in physics and astronomy from the University of Aarhus in 1998, and his master's and PhD in meteorology, oceanography, and geodesy from the University of Copenhagen in 2005. He was a research associate at the Danish Meteorological Institute before joining NCAR originally as an SP postdoc in 2006. He has had extensive contributions to community atmosphere models, including CAM. He is leading efforts in comparing dynamical cores in CESM for the development of CESM3, and involved in CEMA activities, such as leading the implementation of MPAS in CAM. Peter's other research interests include dynamical cores for weather and climate models, advection and transport schemes, idealized test cases, and physics dynamics coupling. So today he will speak about the challenge of energy budget closure in Earth system models. Peter, the floor is yours.
All righty, thank you, Katie. Hope you all, for those of you in Colorado, I hope you enjoyed the snowstorm this weekend. It also means that the Boulder Valley schools are closed. If you see kids jumping around behind me, that's why. Alrighty, I started to get interested in energy budgets in models about 4-ish years ago, where I did some work with Dave Williamson here in CGD on the detailed budget of the dynamical core and physics dynamics coupling. And after working on that, I quickly realized that if one wants to make the modeling of the energy budget more accurate, in particular a more accurate treatment of water in the atmosphere, the problem gets really, really complicated. So I decided to gather a group of experts to highlight this problem, but also to form collaborations. So to get together with Nicholas Kevelhan in Canada, we applied for funding for a Banff International Research Station workshop, got funded, and we decided to invite a broad group of researchers, both from atmosphere and ocean modeling. So you see that Bill Large was there, Alistair Ackroft was there, and other oceanographers. And in the atmosphere, we both had numerical methods, so dynamical core expert presence, but also parameterization developers such as Vince Larson. And we're probably working on writing a paper based on our discussions at this workshop. So in particular, for the presentation I'm giving today, I'd like to acknowledge the many Zoom calls that I've had with Almut Gassmann, who works at IARP in Leipzig in Germany, Thomas Dubas at École Polytechnique and LMD in France, and Chris Eldred from Sandia, and Bryce Harrop from PNNL, and then more recently, I've had a lot of discussions with Thomas Toniazzo, so I'd like to acknowledge all their input and discussions. So why am I interested in energy budgets? Well, here's one motivation. So this plot here shows a term in the energy budget that we're currently not treating rigorously, meaning that we fix this energy budget discrepancy by using an energy fixer. So in other words, we're increasing or decreasing the temperature everywhere uniformly to balance this term. So this term here is related to how we treat water in the atmosphere. I just want to highlight that it's pretty large error, globally 0.3 watts per meter squared, but regionally it can reach about 20 watts or so per meter squared. And just for a comparison, Earth's energy imbalance due to climate change is roughly 0.1 watts per meter squared, or the energy budget after big volcano eruptions is about 1 watt per meter squared or so. So these discrepancies in the energy budget that we are fixing are not small. If we then naively think increasing resolution, in this case horizontal resolution, will alleviate this problem, well, then I have bad news. The problem is the same or even worse. So if you see, if we go to quarter degree horizontal resolution, same number of vertical levels, the structure of this budget discrepancy is about the same. There's just more detail now since we're at higher resolution. So that's a motivation for looking into energy budgets in models. Here's an outline of my talk. So this talk here, I'm basically going to talk about one equation the whole time, and that's this equation up here. So the energy change in the atmosphere is by flux form conservation. That should be balanced by what goes out the top of the atmosphere and what comes in through the surface components. So what I'm going to be talking about in this seminar here is what are these terms. So I'm going to start simple by looking at the total energy equation for a dry atmosphere, where there's no ambiguity in the literature of what that should look like, although there are some misinterpretations that I would like to clear away. Then I'll go in and look at what are these errors in CESM, CAM, in the dynamical core and in the physics dynamics coupling layer. And after that, I'm going to add all kinds of forms of water to the atmosphere. And this is where things start getting complicated. So I'll start deriving what this energy equation looks like in the presence of water in the atmosphere. And then I'll go into the details of what approximations we're making in CAM. And thereafter, I'm going to assess different budget errors in that system. And that will give us some insights in what our path forward could be if we wish to have a more accurate energy budget treatment in our model. I'd also like to highlight here the energy for the atmosphere. We actually, or the equations for the energy of the atmosphere at all scales, we actually don't know. I'm only going to talk about the energy associated with what I call fluid equations of motion, so that the energy conserved by whatever equations of motions we're using in the system. So I just like to highlight that I'm going to make that assumption immediately that EATM is EFEOM. Also, I'm not going to talk about how the scales are being separated in the model, where we have a subscript scale and resolve scales as well. And the interaction between those two is very complicated to deal with rigorously. Alrighty, so given a fluid in the presence of gravity and rotation, the energy of this fluid is given by this equation here, where we divide we put the energy into three terms. So we have the kinetic energy, which is the squared velocity component times half. Then we have an internal energy, and then we have a geopotential energy. And what these terms look like depend on what assumptions we are making. These assumptions, we can categorize them into different categories. For example, geometric assumptions. Are we assuming a spheroid georoid, or are we assuming a shallow atmosphere, for example? And that really impacts this term over here. Then we can make dynamic assumptions, for example, the quasi-hydrostatic assumption of Boussinesq assumptions. And then there's a bunch of thermodynamic assumptions that one can make that I'll get into the details of later in this talk. So what does this energy look like in CAM, a dry version of CAM? So here I'm assuming that we're using the dry hydrostatic primitive equations. So the only thing that changes here in the formula is when we don't allow vertical motions, they're diagnosed. Our kinetic energy is just a horizontal component. How we use a non-hydrostatic solver, this will be in 3D velocity. The internal energy, when assuming a single component fluid, and we assume it's an ideal perfect gas, is given by the heat capacity at constant volume times temperature. And since we're making the shallow atmosphere assumption here, then the geopotential term is simply gravity times height. It can then be shown, it was shown by Akira Kasahara, who also worked here at NCAR back before I was born in '74. And he basically showed when you're using the primitive equations of motion and you're assuming a constant pressure at the top, then this energy here can be written on this form here. So we still have a kinetic energy component, but now the internal and geopotential energies are written in terms of these three terms here, where the two first terms are actually the specific enthalpy. And why I'm writing in this form will become clear in just a moment. There are some misconceptions around this formula for energy here that I'd like to highlight. Since we're taking the mass-weighted integral of this quantity here, it's tempting to regard that as the total energy per unit mass. But just to make absolutely clear, that is incorrect. In deriving this formula here, we've done integration by parts, and we have assumed some boundary condition at the top. And in this case here, pressure is constant at the lid. Alrighty, so using this, using the hydrostatic dry primitive equations, what are the energy errors in a typical dynamical core? So again, we coded, so David Williamson and I, we coded up detailed diagnostics in the dynamical core to assess the energy budget of the dynamical core. And it will always depend on the details of the dynamical core of what this budget looks like. But in the case of the spectral element dynamical core, we can divide it into these three categories here. We have the horizontal inviscid dynamics, where we're just advancing the dicore without any diffusion operators. Since the spectral element method is mimetic, it conserves total energy to time truncation errors. So the errors in this term here are very, very small. All models need some control mechanism to keep waves at the grid scale under control. In this case here, we're using fourth order hyperviscosity and Laplacian damping at the model top. And I would like to highlight, and this is important in this budget, is that we add the dissipation of the velocity components, which is equivalent to kinetic energy change. We add that back into heating, so it actually doesn't appear in our budget. The formulation of the spectral element dynamical we're using is based on vertical remapping. So every so often we map from Lagrangian levels back to an Eulerian reference levels, and that's not total energy conserving. So on the right-hand side here, I have a dry simulation. I'm using Hell-Suarez forcing. The total energy dissipation of the dicore is 0.03 watts per meter squared. So it's very small. You can then break that down into all the different terms. This error down here, that's a time truncation error. So you see it's minuscule. And the other errors are basically divided in two. The horizontal and the vertical errors here are exactly the same. And if you break down the viscosity errors, which is done down here, you can divide it into how much energy is dissipated by applying the del4 operators. This is the frictional heating we're adding back in. So we're adding most of it back in locally. So that means that our total energy dissipation is actually really small. And also to keep the model stable, there's some kind of sponge layer diffusion at the model top, but again, that's extremely small in the grand scheme of things. If we then run the model at higher resolution, go to quarter degree, so I'm only increasing resolution in the horizontal, not vertical, then all the horizontal terms here, as expected, do decrease quite a bit. So the total energy budget in the horizontal converges with increased horizontal resolution. However, I would like to caution against looking at energy conservation in highly idealized settings. And one reason being is that when you add in real world topography, there's going to be a lot of forcing near the grid scale that's going to activate our diffusion or filtering operators, leading to more total energy dissipation. So if we take the exact same test as we just ran and add topography, we get these numbers on the right here. I won't go into the details here, but I just wanted to point out, and now we're going from 0.03 watts per meter squared energy dissipation to about 0.14, so a drastic increase in total energy dissipation. And if we then go to the real world, where it's not only topography that forces the dynamical core at the grid scale, but also physics, then we get these energy numbers here. This is from a regular AMIT simulation. So now the energy error is almost doubled. And again, I won't go into the details, but if you have questions regarding this, we can talk about it after the seminar. So what are the energy dissipation of other dicores in CESM? We've done a pretty detailed budget analysis of FV3 as well, but the total dissipation of that dicore is about 1.1 watts per meter squared. And interestingly enough, that dissipation is the same as the predecessor of FV3, the finite volume model defined on a lat long grid. And I'm currently working on what the energy dissipation numbers are in MPAS. So I hope to be able to show that soon. So that's the dynamical core by itself. We need to couple it to a physics package. So that means we do have tendencies that we need to add to the dicore. If we do, as we do in a finite volume model and FV3 model, we just add all the physics tendencies in one go before we start running the dicore. And if we do that, there are no physics dynamics coupling errors. Unfortunately, if we do that with a spectral element dynamical core, there's a huge amount of noise in the simulation, as illustrated by the absolute value of the surface pressure tendency here, which is basically noise, meaning that the tendencies are simply too large out of balance for the dicores. So there's too much noise in the system. So therefore, we do what I call dribbling, meaning we just add increments of temperature and momentum forcing into the dynamical core throughout the integration. And if we do that, then we no longer have excessive noise in the simulation. For tracers, one has to be really, really careful here if one wants to not mess up the mass budget. So therefore, we just do a state update for the tracer. So the energy errors associated with this process is about 0.5 watts per meter squared. So somewhat small in the grand scheme of things. So what do we do with all these errors here? Well, we let the fixer take care of it. So here's the global energy budget in CAM. So we can divide it into different components. So we have the dynamical core component right here that I've just discussed, where physics dynamics is coupling here. Then we may have a term that's due to the differences in the energy formulas used by the energy fixer, by CAM physics, and the dynamical core. So for example, one may use a different heat capacity for water vapor in the dynamical core. If one does that, we have a discrepancy of about 0.5 watts per meter squared compared to physics that uses a dry heat capacity for everything. There may also be differences in the vertical coordinate and the assumptions made in the energy formula that can also lead to energy discrepancies. And I'm currently working through the details of that in CAM MPAS, because that's based on a constant volume and not constant pressure assumption. All right, this is the dry primitive equations. Now let's add moisture to the mix. So in the last decade or maybe more, we have moved to much more advanced microphysical schemes for examples, and that means that we have added many more prognostic water species to the system. So in the discussion here, I'm going to assume that moist air consists of dry air, water vapor, cloud liquid, cloud ice, rain, and snow. And I actually forgot to add grapple here, which we also have in CAM, but it doesn't make a big difference in the equations I'm going to show here. It's also in the equation I'm going to show, we want to separate just a set of water species. I'm just introducing your notation here. So the H2O just refers to the water parts of moist air. Then I have to make some further assumptions here to keep the problem tractable. So I'm going to assume that all constituents have the same temperature. That gets rid of a lot of issues in the formulation, so make it less complicated. Also assume that all constituents move around with the same barycentric velocity. And I still assume that moist air is an ideal perfect gas. So in the presence of all these forms of water here, then my ideal gas law looks like this. So pressure is equal to the density times the gas time constant and the virtual temperature. And now the virtual temperature is a function of all components of moist air. And the mixing ratio here, I'm not using specific mixing ratios in this presentation. I'm using the dry mixing ratios. Here is just the density of whatever species you're looking at divided by the density of dry air. The advantages of using a dry mixing ratio is it doesn't change if water changes in the column. Alrighty, so the question now is what this equation looks like with all the water in there. It's pretty straightforward with the kinetic energy term. The rho here just changes to the full rho. The phi s term, same thing. We just get a full rho multiplied by the phi s term. But now the specific enthalpy gets a lot more complicated. There are many ways that people derive this. This is how I do it. So a specific enthalpy of a moist constituent can be written on this form here. So it's written in terms of some reference enthalpy with associated reference temperature. So that means the enthalpy of moist air is simply the sum of all of these enthalpies for each component of moist air. And if I expand the right-hand side, then I get this equation down here where I've gathered all the liquid terms and ice terms here. So the density of liquid here would be the density of cloud liquid and rain, so the liquid forms of water, and rho ice here, the frozen forms of water, so cloud ice and snow, and similarly for the heat capacities. So only enthalpy changes have physically relevance. So we would like to write this in terms of physical quantities such as the latent heat associated with phase transformations. So therefore, we're going to rewrite this equation in terms using Kirchhoff's equations, which are written here for different phase transitions. So for example, latent heat of vaporization, liquid to water vapor is written on this form here, where LV00 here is now the difference of the reference enthalpies. Similarly for sublimation, where we go from solid to water vapor. And then again, similar for fusion, where we go from solid to liquid. And please note that the latent heat for fusion can be written in terms of latent heat of sublimation and evaporation. So I write the equation on this slide here now in terms of these physically relevant quantities, and then I end up with these equations here. And in the literature here, there's some ambiguity of what reference state is chosen. So here, for now, I've just written down what the equations look like using 3 different reference states. So one for water vapor, liquid, and ice. And you see they differ in terms of this term here. So if we're using water vapor, this is all based on water vapor terms, and here's all liquid, here's all ice. And along with those changes go the latent heat terms here in terms of if it's evaporation, sublimation, or fusion. I can get rid of this term here already now if the dry mass of the atmosphere is conserved, which it is in CAM. So that means when we say it's taking the global integral here and taking the time derivative, these terms go away. So let's just get rid of them to get the equations to look a little bit more tractable. So now the equations look like this. In CAM, ice is used as the reference state, so I'm going to continue my derivations using this formulation here, but you could mathematically equally well use these other reference states. Probably nobody use a water vapor reference state because it doesn't really make sense for our other components who don't have water in that form. Alrighty, so I'm now going to insert this specific enthalpy into the energy equation. So it means it now looks like this. So these are the terms we had before from the dry energies, and then now we have these extra terms here. And right now it's convenient if we choose a 0 reference enthalpy at 0 degrees Kelvin, because then this term here goes away, so we don't have to worry about it. If one does not choose a 0 enthalpy for this term here, then there will be a boundary flux term compensating for it. And when I derived this equation, I got a little nervous because this equation did not look like an equation for pseudo energy that I derived a couple of years ago. But if one assumes there are no fluxes in and out of the column, then expand these latent heat terms, then one can show that the total energy is in this form here, where the heat capacities here are summed up over all the different water species, which is a little bit like written in between the lines in this formula here. So there is consistency between the different formulations. But it does require that the latent heats are a function of temperature and not constant. Alrighty, so that was just for the atmosphere. There's obviously fluxes in and out of the system. So I'm first going to discuss fluxes from the atmosphere to the surface that can happen in the form of liquid in terms of rain, in terms of ice, or snow in terms of ice, and then in terms of deposition through dew or rime of the water vapor. But the flux can be written on this form here, where M with the dot over it here is the flux of water species from the atmosphere to the surface. And again, with enthalpies, we have to associate it with a temperature. So the temperature of the atmosphere at the surface is denoted TA surf here. So if you expand that term using ice as a reference, then you get this expression here. And then you can do exactly the same exercise for fluxes from the surface to the ocean. This way we can have liquid entering as spray, we can have ice entering as snowdrift, and then water vapor entering as evaporation. And you can do the similar derivation as I did before, now with the surface temperature from the surface component, and the fluxes the other way. So if I add up those two, then I get the net flux from the atmosphere or into the atmosphere at the surface. So it's this rather long equation here. This system of equations here, or this equation, can be simplified a lot if we assume that the temperatures in the atmosphere and in the surface component are the same at the interface. So if we do that, let's call it T tilde, then these terms here collapse into just 3 terms. Also, I've assumed a 0 reference enthalpy, so this first term here is gone. There was fluxes at the surface. There's obviously other fluxes in the system. So if you look at the total net flux in the column, in addition to the surface exchanges, there will be a turbulent flux or sensible heat flux at the surface as well. And then we have the radiative forcing as well. And then I've added, just a residual term here, which is forcing associated with processes that we're not accounting for. So now putting all of what I just said into the equation, then I arrive at this total energy equation for the atmosphere that includes all the forms of water. So now let's start simplifying this system. So this is what I could call, quote unquote, the unapproximated energy equation. It is customary to assume that the latent heats are constant. Please note that assuming that the latent heats are constants is the same as assuming that the heat capacities for all forms of water are the same. So you can choose whatever you like, but they all have to be the same. So that means that these terms here all become constant. In CAM, we're making further simplifications. First of all, we assume that the total water content in these terms here is just water vapor. So that means that condensates do not contribute to kinetic, internal, geopotential energy. They are massless. We also assume that the total water content in the atmosphere here, in these terms here, stays constant during physics updates. Then we discard the enthalpy flux at the surface. So this term here, we're getting rid of that. I'll return to that in a moment. And then we assume that the heat capacity of dry air for all forms of water in the system. So if we make all of those assumptions, we get this formula here, which is the energy formula used in CAM. All right, so there's a lot of complexity here. You have to remember, all of physics satisfies this equation here. The dynamical core satisfies this equation. So there's a lot to untangle here. Just want to note a couple of things to familiarize you with this equation. For example, let's say we have a phase change happening from water vapor to cloud liquid. That means that this term here and this term here remains constant. We're just moving from one type of water to another type of water. So that means that the kinetic energy and this term here does not change. It's a bit different story for falling precipitation. I'll return to that in a moment. If there's mixing of momentum in the vertical, then you'll start, changing this term. So you would need a compensating change to still satisfy this equation. Could be a temperature change. But whatever goes on in physics, each parameterization in theory should satisfy this equation. We also, it's implicitly assumed here that if precipitation is formed, we're not tracing it as it falls out of the atmosphere. It just immediately arrives at the surface and goes out of the surface. And we're only accounting for the latent heat terms associated with that process and not the enthalpy term. This system here is energetically consistent. And as we'll come to know, it was very cleverly chosen by the developers to keep the energetics simple. So just to give you an idea of what the different terms look like in this equation, I'm plotting here a 1-year average in AMIP simulations at 1 degree with CAM6. You see the left-hand side here of the equation plotted here, and then the right-hand side of the equation here. Since CAM satisfied the equation above, if you take the difference between the two, you basically get 0 as expected. We may further look into what the right-hand side can be broken into. So if we take the latent heat terms, they're plotted on the right-hand side here, and they're positive almost everywhere. And on the right-hand side, that's where you have the sensible heat flux and radiation. At first, when I produced this plot, I was a little surprised that the latent heat flux terms are all positive, because these terms here are not always positive, as shown on the right-hand side here. This is the flux of water. You see it's a positive in the evaporation zone, negative in strong precipitation zones. But since the latent heat of sublimation written on the right-hand side is about an order of magnitude bigger than that of fusion, that means that this term here totally dominates. So that means that if you add up the two terms, since it's dominated by the positive term, then the total of the latent heat term here is positive. Alrighty, so now I've given you a feel of what the different terms here look like. Now it's time to undo some of the assumptions that are made in CAM physics and see what the effect is. And I'm just passively diagnosing what the different terms are in line in the model. So that means that the model simulation will not change subject to those changes. So it's just diagnosing what's going on. For example, let's include all forms of water in the total water term. So it means these terms here now includes all the condensates. And if we do that, the mean change is, as expected, very, very small. And regionally, changes are larger, but not very large. They're down to like 0.03 watts per meter squared at most. Again, I haven't let any water escape the atmosphere here. So this energy change here, if we were to implement it in the model, that would stay in the atmosphere as a heating or cooling term. If I now go in and say, hey, I want to use the heat capacity for water vapor in this term here, instead of just having using the heat capacity of dry air for everything, then I get a much larger effect. I get about 0.3 watts per meter squared. Again, these are not flux terms of what goes out of the atmosphere. This remains in the atmosphere. Then I can go in and say, okay, now I'm going to let the total water in the column evolve. So that means now I'm going to take into account that water actually falls out of the atmosphere, comes in to the atmosphere. Let's just look at the kinetic energy term first. This is kinetic energy, probably mostly lost to the surface. And there you see that the regions of precipitation and high surface winds, really show up in this plot. But again, very, very small term. The much, much bigger term is the one where I let water vapor, total water change in the columns. This is the internal energy and geopotential energy associated with the water fluxes in the system. And now I get this 0.34 watts per meter squared. So it's very similar to the plot I showed on my second slide. So now let's add the enthalpy flux term at the surface in here. So let's compute what this term looked like that we got rid of in CAM. Now I need to choose a temperature here. I'm just using the TS, the surface temperature that comes out of the model. So that's the radiative temperature. So basically the temperature of the surface component. And if I plot that and now plot what I had on the previous slide next to it, you see that these two terms look very, very similar, although their averages are quite different. The structure here is quite different, is quite similar. And if I take the difference now, take this plot and subtract it from the other plot, then I get this. And now the scale down here is much smaller. So for example, in the evaporation zone where we had about 20 watts per meter squared energy imbalance, we're now down to, the zoom bar is in my way here, so I can't see the plot. So it's down to about 0.8 watts per meter squared here. So we've drastically reduced this imbalance in these regions. And similarly in these precipitation zones. So these two terms here are definitely related. But you may ask, why are they not matching up exactly? Well, in fact, they shouldn't entirely match up because think of, for example, precipitation where water falls out of the atmosphere. There's probably some of that energy of that droplet falling to the surface that stays in the atmosphere or interacts with the atmosphere. That's not included here. So there may be frictional heating of the falling rain. There may also be rain slowing down winds, and you can make similar arguments for evaporation. Also, we have assumed that in the surface enthalpy term, if you remember, if we write it out with not assuming that the temperature in the atmosphere and in the surface component is the same, then we have many, many more terms here. We have to remember, we just assume that water vapor enters the atmosphere at the same temperature as precipitation leaves the atmosphere. Nevertheless, you can ask the question, well, what should this T tilde be if these terms should match up exactly? So I've computed that here on the right-hand side, and my apologies that the plot is a little bit messy, but I had to choose some threshold value for which we're not computing this term, so where the water vapor flux is really, really small. So those areas are just in dark purple, so just pretend these, don't look at those areas at all. And what I plotted here is then the TS term that balances, the T tilde term that makes sure these terms are balanced minus the surface temperature that I've been using. And as you see, in most regions, the temperature has to be about 10 Kelvin colder than the surface actually is. So reducing this temperature used for this term here actually makes sense, at least in some regions. For example, if you look at the Pacific evaporation zones here, the atmosphere is colder than the ocean, so it's probably consistent, or it is consistent to have a cooler surface temperature here because the water vapor enters the surface here that's colder, so one could assume that the temperature is lower. Also, for the larger precipitation zones, there was an observational study from 1998 that just looked at observation in the Pacific warm pole regions, and they actually showed that the droplets, when they reach the surface, are about 5 degrees colder than the SST. So again, here, that's aligned with using a smaller T tilde in the calculations. Alrighty, time to summarize here. So I hope I've convinced you that it's important to look at total energy budgets, and there can be compensated errors in the system. An example of that is CAM spectral elements. If you were to just look at the energy tendency from the energy fixer, you might think that everything is really, really well balanced because it's just off by 0.02 of a watt per meter squared. But if you actually go in and do the actual budget, you see that we have very large compensating errors. So we have this dry mass adjustment. That was the term where we include water vapor changes in the column. That's about 0.3 watts per meter squared. And then the energy dissipation of the die-core is about 0.24 watts per meter squared. And then the physics dynamics coupling is about 0.05 watts per meter squared. So large compensating errors that we wouldn't know about if we hadn't done the analysis. Dynamical core errors are large. In the physics, probably the biggest error we currently have is the surface enthalpy flux term that we're currently neglected. We should probably not do that. However, there are a lot of details to be worked out on how to formulate that term. These results here also gives us some indication of where we should focus our efforts if we wish to have a more accurate representation of the energy budget in our model. So even though a lot of effort has gone into dynamical core solver research in the last decade or two, we're still not done if energy conservation is important to you. And there is currently quite a bit of work going on with using Hamiltonian dynamics where one can reduce these energy errors even further. And on the physics side here, we should move towards a more consistent and accurate treatment of the moist thermodynamics, or mostly the moist thermodynamics. So as I mentioned, we shouldn't ignore the surface enthalpy flux term. We should probably change to a more comprehensive formula for energy. That means we have to make the latent heat a function of temperature. If we do that, then we have to have the heat capacities with the correct heat capacities associated with the different forms of water. We should include all forms of water in the density on the physics side. And in order to make the physics less error prone, I've been advocating that we move to dry mixing ratios because they stay constant when there is water changes in the column. We probably also need to make changes to individual parameterization. The extent of this is unknown to me. But in theory, all the parameterization should use the same or consistent thermodynamics. And one discrepancy that we do know of, for example, is that club uses different energy potential than what we're using in the rest of CAM physics. So that leads to some discrepancies. So ideally, the parameterization should all call libraries or be passed functions to compute thermodynamic variables so that all parameterizations are using the same thermodynamics. I don't know if it's possible, but it will be nice to move to a coding paradigm that could allow that. We should also most likely consider specifying the thermodynamic quantities in terms of thermodynamic potentials like enthalpy or Gibbs potentials. And if we do that, then the thermodynamic properties of the system can be derived by them. So you're always sure that all your variables, thermodynamic variables, are consistent if you do that. And with that, I'll take questions.
Thanks very much, Peter. Yeah, we have plenty of time for questions. Well over 100 people on the Zoom right now, so I'm sure we'll have a lot of interest. Julio has a question. Go ahead.
Hi, Peter. Thanks. That was really interesting. I was interested in your last point about the temperature of rain.
Mm-hmm.
You seem to suggest that the rain, like I guess is intuitively clear to most people, is colder than, well, it's often colder than the surface, but is it colder than the air in which it's falling? And that's probably more a question for the microphysics people. But are we you know, are you suggesting that we have separate, I mean, should we include a separate temperature for falling hydrometeors? That would, I guess that would involve changes to the microphysics. Is this, I mean, is this a subgrid temperature variability in which the rain in rain showers is at approximately the same temperature as the air they're embedded in? Well, I'm just wondering where to go with that point.
Julio and Peter, if I can jump in, yes, because droplets evaporate when they fall towards the surface, they are colder than the air, and they can be substantially colder than the air. And in fact, in Toga Core, there was a small project, I think Peggy Lemon looked into that. And the fact that this colder droplets cause lenses of kind of colder water sitting at the surface, these were observed. So I think this is really true that this happens in nature. So this is not some speculation that has been observed in Toga Core during this big field project.
Yeah, thanks for that input. Yeah, so Julio, it's really a can of worms here. Like we don't have separate momentum equation for the condensates. We have assumed they have the same temperature in the atmosphere, so we would like to move away from that. The system gets really, really complicated. So again, in terms of the energy budget, it all comes back to this T tilde here. But I think what you're referring to is that maybe we need to split this surface enthalpy term, which is shown here, this term here. Like we shouldn't use the same temperatures for the surface coming from the atmosphere and from the surface coming from the surface. Because in that case, then we would have a specific temperature for hydrometeors falling out of the atmosphere. And then similarly for evaporation, we would have a separate temperature at which water vapors enters the atmosphere.
Okay, thanks. It looks like.
Yeah, and the thing I have not unraveled in this analysis is also what's the effect of having the latent heat as a function of temperature, because then you get, extra terms down here.
Okay, thanks, Julio. So Andrew Gutteman has a comment in the chat. I'll just read it out loud. In the microphysics, we account for the energy of phase changes with precipitation, but not the evolution of temperature that occurs with falling precip. Another worm for the can. So just something to comment on there. And then I think we'll move to, unless you want to respond to that, Peter, there's another question.
There have been several studies about that, like the frictional heating of falling precipitation. I think the estimates has been around a watt per meter squared or so. So that's one effect. And then there's also the potential energy associated with removing water somewhere in the atmosphere that just falls out of the system. So there are many terms in that, but I still think that this analysis has shown that the way biggest term is this enthalpy term, whereas the kinetic energy associated with the falling precipitation is rather small.
Okay, Raymond, go ahead.
So kind of a broad scale question here with these errors in the energy budget. In practical terms of what we use climate models for, how important are these terms? I mean, are they kind of compensated out or differenced out, or are they really important in making climate predictions?
Yeah, that's a good question. So I tried to be really careful with my formulation here and just like not calling it an error, because our total energy budget at the end of the day is consistent, but we're fixing it globally. So since we're doing that fix at the end here, that means our system will not run off the rails. We can use it for climate change research on large scales. So in that sense, this study does not like invalidate CSM2 and other models. But I think it does highlight that we could do a better job regionally by being more rigorous with these energy terms. And I should also mention there's a rigorous tuning exercise going on when developing these models. So we are likely tuning to compensate for some of these locally energy budget errors. So when we are if we move towards a more accurate description, we most likely will have to retune things because now we're capturing the local processes more accurately.
Thank you.
Great. Matthias Steiner has a question in the chat. I'll read it out loud. I think it's a related question to the previous one. Given all the notable errors you discussed, can we believe climate model results, or what aspects can we trust versus what should we be concerned about in terms of interpreting the results?
I think I partially answered that in the previous answer. I think, again, I think there's no doubt we can trust our models in terms of global budget, global climate change on very large scales. But again, in the small scales, we can definitely do better.
Other questions for Peter? I'm not seeing anything, but I feel like we should give people another minute. Oh, Bill Large, go ahead.
Yeah, just to keep the dead air time down. So Peter, I assume that what you're saying is that if we want to balance, say, just the rainfall into the ocean, we should assume that the rain is coming at 10 degrees minus the surface temperature of the uppermost temperature of the ocean, and we have to then heat it by 10 degrees, and that's an empirical number that you've computed because it accounts for the fact that your rain is dropping. The rain is coming from the level it's formed, and that's multiple levels. So it's kind of mixes all that up. Plus, I suppose, any kind of re-evaporation, it's like an empirical number. And that to do it right, like we've just been talking, is too complicated for now anyway. Is that more or less what you said?
I think there's a little bit of an overstatement. Like we know where the precipitation, let's say a water droplet is formed at some height.
Right.
We know the temperature at which it was formed.
But we don't send that to the ocean, right?
No, but we could, but assuming it doesn't interact with the environment, again, no kinetic energy interaction, no heating of the air parcel as it falls, we could send that directly to the ocean. So, but again, I said that would probably be too cold. But I'm saying we could put stuff like that in there. What I'm saying is the real full accurate treatment of this, where we actually have enthalpy equations we're solving for these water constituents, as well as momentum equations and so on. That's probably too complicated at this point in the stage.
But if we're doing budgets and trying to get a global budget, we should sort of use about 10 degrees right now without doing anything else.
Well, it depends where you are on the globe, but
oh yeah,
back of the envelope, yes.
Yeah, okay.
All right, question from Peter Sullivan in the chat. How big is the uncertainty in F-turb compared to the other errors?
So in the sensible heat flux term here, again, There's also assumptions made there. For example, there's no sensible heat flux due to rain at the surface. There was a recent paper about that. And I can't remember on the top of my head, so please don't quote me, but I think in the global balance, it didn't matter, but locally it could be a couple of watts per meter squared doing heavy precipitation events. So there are definitely also other terms here that we could consider if we were to try and rigorously include this term here as well.
Okay, Raymond, go ahead.
So kind of another broad question. Some people are worried also about the global and local entropy budgets in the atmosphere. And what's not clear to me, I mean, they may be as important as the energy budgets, but what's not clear to me as to whether, how much of the entropy budget you get right if you get the energy budget right, and how much is an independent variable. I mean, this is kind of off topic, but I think it's also important to global models, potentially.
Yeah, it's a bit like mass conservation and transport scheme. Just because you conserve mass doesn't mean it's accurate. Just because you're closing your energy budget doesn't mean that you're getting a accurate simulation. Like I could go in here and just choose T here so that these two balance, and then I can say, well, now the energy budget is close, which is true, but it might not be accurate because I didn't take into account various processes that we've been discussing. So yeah, one should be careful exchanging accuracy with conservation.
So maybe entropy is an even bigger can of worms than energy.
Yeah, well, it's a thermodynamic potential, and yeah, it's a can of worms.
Other questions for Peter? We have a couple minutes left. All right, I'm not seeing anything else, so I think we'll wrap up. Thanks so much, Peter. Just so everyone knows, we're not having a seminar next week because it's spring break